Yeah, it's possible. Where are you?
A gente tá mostrando.
Okay.
Hi.
Sometimes for
tela
1 week, more or less.
Good luck.
Very nice start, Yohann.
Hi, good morning. We are finish it up in here. We're starting soon. We can listen you well. Just a minute, please.
What? I didn't hear anything. Something from BCM Singularities?
You didn't hear me?
Not very.
Not so well?
It's better. Maybe
it's better now?
Now it's okay.
Okay. We are finishing up in here in 2 minutes or so. We can start. Just a moment, please.
Okay, I have nothing else to do, so you can you can wait as long as needed.
Okay.
Eu acho que já está na hora, né? Podemos começar já? Okay, so we are beginning the first talk of this day, and the speaker is Professor Yohann Genzmer from the Institute of Mathematics of Toulouse, and he will talk about the Saito number of a singularity of a complex curve. Thank you very much, Yohann.
Okay, thank you. So now I suppose I can start.
Yes.
Okay, thank you very much. So
yes, you can begin.
So thank you very much for the invitation. I know it's quite difficult to organize such an hybrid conference, and I regret not to be in person. And I hope quite soon every kind of conference will be just as usual. Okay, but let's say we are going to speak about this notion, the Saito number of a complex singularity of curves. So in the first part of my talk, I will introduce this concept for any hypersurface in any dimension. But quite soon, I will restrict myself to singularity of curve, because this is actually the only case for which I am able to say something interesting. Okay, and just for the record, this is not, the picture is not the Institute of Mathematics of Toulouse. Okay, this is a city hall, actually. Whatever. Okay, so let's start. Sorry. So Saito module and Saito number of an hypersurface. So consider a germ. So my point of view are going to be strictly local. So consider a germ of hypersurface in the complex plane of dimension, in the complex space of dimension n, which is given by some function here, and you can suppose that f is reduced and belongs to the set of analytical germ of function. Analytical germs of function. I will denote this set O of n just for simplification of notation. Okay. So now there is a module associated to this hypersurface, which has been introduced by Saito probably in the 70s. So this is the module. This is an ON module, right? Which is usually denote der log of sigma. Der means for derivation, and log is to refer to the theory of logarithmic vector field. This is actually the module of logarithmic vector field for sigma, which is just the set of germs of vector fields tangent to sigma. So in that context, what means tangent to sigma? This is actually the following property. If you take a vector field x, which is just written this way, so here the function, the coefficient ai are just series in n variables. So this, we are going to say that x belongs to this module if and only if you apply x here as a derivation, the derivation of x applied to f, x as a derivation to f lies into the ideal generated by f. Okay. Well, but of course, this is just because we usually consider the case of an hypersurface which is singular. But if you are at a point where sigma is just regular, then being tangent is just being tangent. Okay, x is just tangent to the hypersurface. So this definition is not really mysterious. This is what I mean. Okay. So the idea is to just for the moment to speak a bit about this ON module. Say something. Give me just very basic example. The first case, which is the simplest one, is when sigma is a smooth hypersurface. Then you may know that up to some change of local coordinates, you can suppose that sigma is just the one of the coordinate hyperplanes, meaning that sigma can be like that, and then you have some conjugacy, which is an element of diff of Cn, the germs of local change of coordinates that send sigma to just x1 equal to 0. So in that case, this is really easy to describe precisely the Saito module, the Saito of tangent vector field to sigma. This is a free module, which is not absolutely, which is usually not the case. So it's free module. Which is not the case in general. In general, this module is not free. The freeness of this module is a problem that has been studied quite extensively, but this is not my point of view for today. But you can see it's generated by the coordinate vector field here and just the vector field x1, dx1. So you get this hyperplane here. And then you get the generator which are like that. This is dx2, dx3, and then you have the first one here, which is x1, dx1, and which vanished, of course, along the hyperplane, just to be to let this hyperplane invariant. So this is in some sense the trivial case in which I insisted this module is free, and in general, this module for a given hypersurface, this module is absolutely not free. It is finitely generated, but you always have in general some relation. Okay, another example: if you pick sigma to be the union of k hyperplanes, where k is any integer, then you can exhibit an element which belongs to this vector field, which belongs to this module. So if sigma is k hyperplane, then this vector field, which is the sum from I goes from 1 to n of xi dxi, it is actually tangent to the union of k hyperplanes, just because if you apply x as a derivation to the f, which is the equation of this k hyperplane, then you will find that x of f is just kf. Okay, it's a very simple computation. So I mean, here you can exhibit at least one vector field which is tangent to this hypersurface, and in general, it is even quite difficult to exhibit an example, an interesting example. Why this one is quite interesting is because, as you can see, while k goes to infinity, the valuation of x keeps being equal to 1. So what in the talk, what I'm going to mean by evaluation, okay? This is just if you look at a vector field like that, the valuation of AI dxi, this is just the minimum of the valuation of the function, where, so here the valuation is just the standard valuation on the germ of a function. Standard valuation on C of x1, etc. xn. Okay, so this example is interesting because you get a hypersurface whose algebraic multiplicity goes to infinity, while the valuation of the vector fields keeps being equal to 1. Let's go on with the example. Let's keep on the example. Little by little, I'm going to focus on the case of curves, which is the main case for me. So if you look at the curve given by, so we are now in dimension 2, the curve is given by a function f, then you can associate to f this vector field, which is just the derivative of f with respect to x times dy minus the derivative of y the derivative of f with respect to y times dx. So sometimes I think this is called the Hamiltonian of f, and it denoted sometimes just h of f. I'm not sure there is a very, very standard notation for that vector field, but whatever. You get this vector field, and it is an example of vector field which belongs to the set of tangent vector field, just because if you apply x to f, then you get 0. So of course, it lies in the ideal generated by f. So in dimension 2, you can produce always a vector field. You can do this procedure for higher dimension, but in particular in dimension 2, you can produce this way a vector field which is tangent to the curve. Let's focus on a very, very precise example. This is one of my favorite curves. Okay, this is a double cusp. So it is given by the product of two cusps, which are transverse. So it looks like this. Sigma is, you get one cusp like that, and another one which is this one. And you can consider the reduction process, the singularization of this curve, and you will obtain the following picture. So you have the exceptional divisor is an union on five divisor here, d1. Sorry, let's say d1, d2, d3, there is d4 here, and here, d5. And the component here are attached to d5 and d4. So this is the component of sigma. So this is what looks like the singularization process of this double cusp. As you can see, the algebraic valuation of sigma is just 4, because here you have x2 times y2. And in that case, the multiplicity of the curve is 4, and the multiplicity of the Hamiltonian of f is 3. So the difference between the multiplicity of the vector field and the tangent vector field and the curve is just 1. But in some sense, I will show you that you can do better. You can find a vector field which is tangent to the same curve, sigma, but whose valuation is smaller than 3. And actually, this is the following one. Okay, this is much better it's much better to produce this example. You have to use computer actually to produce, to find this vector field, because it is not produced just by a derivative operation. You have really to identify any coefficient and so on. But you can do this by computer. But my point is that you get a valuation which is smaller. When you consider just the derivative of the Hamiltonian of the function, you will obtain 3. And you see that there is in the module of tangent vector field some vector field whose valuation is smaller. This is this remark that led me to introduce the following number that I call, in reference to Saito, that who study a lot the theory of logarithmic vector field. The Saito number of sigma is precisely the minimum of the valuation that you can get for a vector field tangent to sigma. And the whole point, my whole point, is to try to obtain some formula for that number using, let's say, other topological invariant or analytical invariant extracted from the hypersurface. How can we compute S of sigma from other data of sigma? There is some motivation to introduce this number, but I have no time to explain. But it is linked with the moduli space of the dimension of the moduli space of the hypersurface. Okay. And just a very, very simple remark. This is an analytical invariant of the hypersurface, meaning that if you take two curves which are analytically equivalent by some change of coordinates, sorry, I say curve, but here, of course, this is defined for hypersurface. So if you take two germ of hypersurface which are conjugated by some change of coordinates, then they share the same Saito number. And just because, well, you have the two module of tangent vector field are conjugated because, of course, this you get that the valuation, the algebraic valuation, is invariant by change of coordinates. So this is a very simple remark. And I will introduce another concept, which are the vector field, the optimal vector field. So I'm going to say that the vector field is optimal if it reaches the minimum of the valuation, meaning that the valuation of x has to be equal to the Saito number of the hypersurface. Of course, here you require that x has to belong to be tangent to sigma. So it is optimal if it is tangent to sigma and of minimal valuation among the vector field tangent to sigma. So the whole point here of this talk is to say something about this number and try to say something about a vector field which is optimal, something about its topology and so on. Okay. So I'm going to focus now on the case of dimension 2, which means that I'm going to look at an hypersurface in dimension 2, so I'm going to look at a curve. Because actually this is the only case in which I am able to say something until now. But now, this day, I'm focused more on the case of higher dimension, but it seems to be really, really more complicated. Okay. So suppose n equal to, the dimension is equal to 2. So this work starts with a result due to Saito, which is the following theorem, which has been proved by Saito, I think, in 1978. So if sigma is a curve, so if we are in dimension 2, then actually the module of Saito is the module of tangent vector field to sigma, the module of Saito is free. And I insist, again, this is something which is completely specific of the dimension 2. Even in dimension 3 and higher dimension, in general, this module is not absolutely free. So this is very interesting. You have generators. This is really strange. You have two generators. Oh, okay, three of dimension 2, I should say, of dimension 2. And you have a criterion for a couple of vector fields in this module to be a basis. In that, this relation has to be satisfied. So x1, x2 is a basis, if and only if the determinant of these two vector fields, which are just the determinant of the coefficient in any basis, is an equation of the curve. So here, sorry, f equals sigma is exactly f equals 0. So this means in particular that this determinant can be also understood that the locus of tangency between these two vector fields. So it is required that the locus of tangency is exactly the curve sigma equal to 0. So this is the starting point of my result, of my work, this result due to Saito. Let me give you an example. If you consider, for instance, sigma, which is the curve given by the locus of the zero locus of xi plus yb. So here, a and b are any integers, not necessarily coprime. Maybe, let's say, bigger than 1. Not necessarily coprimes. Then you can consider these two vector field, x1, which is called the quasi-radial vector field, and x2, which is just the Hamiltonian associated to f. You can check that they are both tangent to f to sigma, and that the determinant can be computed explicitly. This is ab times the function. This is more or less, as far as I know, the only case in which you can compute a basis so easily. I mean, completely explicitly. In general, this is very, very, very difficult to, very, very difficult. You have to use, computer to obtain a basis for this model. But even with computer, this is difficult. As soon as the degree of the curve is quite large, the algorithm does not manage to finish. The computation are too large. Okay. So from this relation here, I'm going to make a very trivial observation, which is that if you write down xy this way, ai dx plus by dy, then the determinant of x1 and x2 is just this product. And you require, if x1, x2 is a basis, then you know that a1, b2 minus a2, b1 has to be equal to u times f, where u is a unity. And as I said, f is an equation of sigma. So you see that there is necessarily a link between the multiplicity of f and the valuation of the vector field. And actually, you can see that from this relation, that the valuation of the vector field cannot be too big compared to the one of f. If, for instance, if the valuation of a1, b2, a2, b1 was bigger than the valuation of the function itself of f, then this relation would be impossible. And actually, you can check very easily that the Saito number has to be less than the multiplicity of the curve over 2, because here you have a product of two functions. So the multiplicity of the element in the basis has to be smaller than the multiplicity of at least one of x1 or x2 has to have a multiplicity smaller than nu sigma over 2, multiplicity of sigma over 2. So you get an upper bound. My point, my first result is going to precise at what extent this upper bound is rich. And actually, so this is the first result I want to mention. If you consider a germ of plane curve, which is generic in its topological class, I'm going to explain a bit what I mean by generic in its topological class. Then the Saito number has to be one of these three numbers. Of course, the first two, it's when nu sigma is even. And here, nu sigma, it's the equality when nu sigma is odd. You see that there is, when nu sigma is even, there is two different cases, two possibilities. And when this is the first, when this is the second, is something which is absolutely clear in my work. Okay, but maybe at the end of the talk, I'm going to explain when this is the first and when this is the second. So let me give you an example of this result that illustrates this result. In particular, why you had to have this genericity hypothesis. So the main example is the case of 5 transversal regular curves. So imagine that you consider sigma 0, which is the product of 5 straight lines. So here, sigma 0 is given by x, y, x plus y, x minus y, x plus 2y equals 0. So this is the red curve here. You can see there is 5 red curves here. And this is exactly this red curve. Then if you consider this curve, which is the union of 5 transversal regular curves, you can consider this vector field x0, which is called the radial vector field. And its integral curve are depicted here. This is all the black line and the red line, of course. So you can see that x0 is tangent to sigma 0, and its multiplicity is equal to 1. But now the idea is I'm going to make a very small perturbation of sigma 0. And if I do this perturbation of sigma 0, so the perturbation is here, you can see I transform the last straight line into a parabola. So I just add epsilon x squared. Here, epsilon is different to 0. My point is, if you do such a perturbation, then you stay in the same topological class. Sigma 0 is topologically equivalent to sigma epsilon for any epsilon different from 0. So you stay in the same topological class. However, you do not have any more vector field of multiplicity 1, which is tangent to sigma epsilon for epsilon different from 0. Actually, you can show that again with a computer, because this is already very difficult to compute. For epsilon different to 0, if you consider there is an optimal vector field, a vector field of smallest multiplicity as possible, which is written x plus y times the radial vector field plus some higher order term. My point is that here, the multiplicity of x epsilon is equal to 2. And you can see that if we go back to the result, sigma here, sigma, the multiplicity of sigma 0, which is the same as the multiplicity of sigma 0 of sigma epsilon, is 5. So this is an odd number, and you should have mu 5 minus 1 over 2, which is equal to 2. So this is not equal to 1, but in that case, you get a vector field of multiplicity 1. But this sigma 0 here is precisely not generic in its topological class. You have to consider a generic point in the topological class to obtain the bound in the theorem. In particular, you can see that you cannot deform x0. Of course, sigma of epsilon is a deformation of sigma 0, but this deformation of curve cannot be followed by a deformation of x0. Of course, x0 cannot be deformed even continuously. So, of course, all the more not analytically, cannot be deformed into x epsilon, just because the multiplicity jump. So this is just to say that here we are in a situation where the optimal vector field for sigma 0 cannot be deformed in an optimal vector field for sigma of epsilon. Okay. So let's go back to this result. So my point is to now to take some time to give you some idea of the proof of this result. So this is a consequence of two tools. The first is well, let's go. Okay, I'm going to precise the tools during the proof. So let sigma be a germ occurrence. So the first idea is to consider precisely a deformation, a miniversal deformation of sigma. So here S is an hypersurface which contains all deformation that you can imagine of sigma, all the topologically trivial deformation of sigma. And here you have a space of parameter which is of dimension n. And of course, this dimension is very interesting for me, but I have some way to compute how this number, but for now, it's not really relevant. Okay, so it's a finite, it's regular, it's a smooth space of parameter of dimension n, and you have this picture, this commutative diagram, which is so a miniversal. Miniversal means that it contains all the deformation and that the factorization through this deformation is unique. Okay, so you have this deformation. Now the idea that generically, if you pick a generic point in the space of parameter, there exists an optimal vector field xt0 for the slice. So if you slice the hypersurface S over T equal to 0, you get the curve, which is the deformation of the initial one. And you have an optimal vector field for this curve, which means that its valuation is equal to the Saito number. And the main point is that this family is analytic. And as in the example I show you, with the 5 transversal curves shows that you cannot do this on the whole topological class, on the whole deformation. You have to restrict yourself to some generic set into the space of parameters. Okay, in particular, any topologically trivial deformation of this curve can be followed by a deformation of the vector field. So I'm going to translate this sentence in cohomology, and this is where the cohomology tool is going to interfere in my work. The first is to understand, cool. So in 1995, Jean-François Mathématiques showed that the space of infinitesimal deformation of any curve, actually, but in particular of this curve, is identified with the first cohomology group, this first cohomology group, so this is a cohomology which is computed after desingularization. So you have here a map which is a desingularization of the curve. So you imagine you have your curve here. You have the whole desingularization, which can be quite complicated. This is the set, the space, total space of the deformation. And here you have a sheaf, which is the sheaf of vector field tangent to the total transform. And you can compute the H1 of this sheaf. And actually, it can be, Mathématiques showed that it can be notified with a space of infinitesimal deformation of the curve. The second tool is the same idea, but with vector field of foliation. So in 1988, Javier Gomez-Mons shows that the space of infinitesimal deformation of a foliation induced by the vector field is identified with the first hypercohomology group, this one. So here we have to use hypercohomology of a leaf complex associated to the foliation. So I have no time to explain you what is a leaf complex and so on, and precisely explain what means here. Just the whole idea is that I can interpret in a cohomological way the space of infinitesimal deformation of the curves and of the foliation. And as you may remember, here I said that any topological trivial deformation of the curve can be followed by a deformation of the vector field, which means that there is some map which is onto. And precisely, there is actually an exact sequence. Here you have, in some sense, the deformation of xt0. Here the deformation of S restricted at t equal to 0. And you can prove that there is an exact sequence where here you find the first cohomology group of a certain sheaf. I cannot explain which sheaf, but whose cancellation can be shown to reduce to the inequality we are looking for. So here, actually, this is H1 of some, the sheaf here is a sheaf of some kind of two forms, of analytic two form. Okay. I don't want to enter into too much in detail, but the whole point is that this is really, the cohomological tool here is absolutely necessary to obtain this boundary, which is more or less the theorem. Yeah, there is this -1, but you can after that make some kind of trick to obtain exactly the result. So this is the idea of the proof. So now we have this theorem, which says something about the Saito number. And now I want to identify, to say something more, not only about just the Saito number, but about the optimal vector field. So I want to say something about the topology of an optimal vector field. So let's go back to another example. Consider this curve, which is the product of 3 cusps, again, cusp. But now the cusps are tangent, okay? So the curve looks like this way. 3 cusps, like okay, here, 1, 2, and the third, more or less this way, okay? And the idea here that the reduction process looks this way. So you get three components, D1, D2, and D3. And on the last component, which is D3, you obtain here after, so this is the total transfer, the strict transform, of course. All these curves are attached to D3. All the components of sigma are attached to D3. So there is a way to describe with some numerical or numerical invariant to describe this situation. So one of the standard way to describe this situation is to associate to this situation a graph which is what we call dual graph of the desingularization. So this is really classical construction. And each point here corresponds to an irreducible component of the exceptional divisor. So you have D1, D2, and D3. And there is a link between 2 points. There is an edges when there is a meeting point. Okay. You can associate actually to this. There is another way to describe this data, which is what we call the proximity matrix. So this is a matrix that describes the sequence of blowing up. So this is a matrix which is always upper triangular. So here, this tie is 3 because there is three exceptional component in the exceptional divisor. 0, and then you have some -1 here. This is this one, and here there is this corresponds to D1, D2, and D3. And the fact that there is here 2 - 1, the 2 - 1 are here because D3 is obtained by blowing up a point which is the intersection of D1 and D2. Is here to encode the fact that the D2 is a blow up, sorry, D3 is the blow up of D1 intersect with D2. Okay. You can also, so this is a way to describe the reduction process, this matrix. You can also now describe the curve by associating to each component here an integer, which is the number of irreducible components which is attached. So here you have 0. There is no component of sigma attached to D1, no component attached to D2, and 1 component attached to D3. So now what look like the optimal vector field in this situation? You have this picture, and now you want to look at the optimal vector field associated to sigma. So actually, it looked like this. So what I draw in black here are the integral curve. So you see that if I take again this dual graph, so this is still D1, D2, sorry, D3, D2. You can attach some more bunch of integers to describe the topology of the vector field. You can see that, for instance, D1, the vector, the component D1 is actually invariant by the vector field. This is a leaf of vector field. So to encode this, we are going to introduce an integer which is equal to 0, 1, depending on the fact that the component is invariant or not. Since D1 is invariant, I'm going to introduce delta 1, which is equal to 1. And you see that you have the same property for delta 2. And delta 2 is equal to 1, it is invariant, D2, and delta 3 equal to 0, because here you see this vector field here is transverse. The integral curve of the vector field are transverse to this one. And finally, you can attach some more integer. Here we have some invariant curve, which are, this is a blue curve, which is not in sigma, but which is still invariant by the vector field. So we are going to count how many curves there is attached of this kind to D2, and we are going to associate an integer, epsilon 1, epsilon 2, epsilon 3. So epsilon 2 is going to be equal to 1 because there is 1. Epsilon 1 is equal to 1 also. And on epsilon 3, I'm going to count the number of leaves which are not exactly transverse to the exceptional divisor, but precisely tangent. So here, you have one. So my point is that these data describe the topology, part of the topology of the vector field. And now the idea is to make link between all these topological data. So this is the last theorem I want to show you today. Remember, in general, you have a proximity matrix of the desingularization. Here, some integer which describes the curve sigma. Some integers which are in 0 and 1, which describe whether or not the vector field is transverse or tangent to the exceptional divisor. And some integer that count the point where there is an invariant curve transverse to the exceptional divisor or tangent. And then there is this theorem, which is quite difficult to express, but my point is that you have a link, which is this relation. So P is the proximity matrix. So here you have kind of linear relation between the vector field which contain this data, the epsilon data, and this vector field which contain some information about the foliation, this delta k. And here, these are the multiplicity of the successive curve blow-up point after point. Okay? And you have some compatibility condition. My point is that there is a very precise way to obtain this information. And what is important is that this system is, the solution of the system is unique. So the system is give without any ambiguity the topology of optimal vector field. Okay, and then it gives rise to an algorithm that allowed. So if I take just 1 minute to show you this algorithm.
Okay.
So I'm going to share something else. Okay, so I hope you will see. Does it work? Okay. So
Yes.
here, this is a little software that I wrote to play with curve actually. So you are going to see this is very, very funny. So this is the first exceptional divisor, and then you are going to describe, you are going to describe blowing up after blowing up some curve. So this is a reduction tree of some curve. And then you are going to attach to say, well, there is some curve here, 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 and let's say 2 here, 1 here, and 1 here. So this is a curve. This is a reduction process of some curve, any curve. And you can now ask for some invariant, for instance, the algebraic multiplicity. So you can see this is 41. Okay, so the multiplicity is 41. So maybe I'm going to share my whole, yeah, this is going to be better. No, sorry. If I do this, okay. Yeah, it will be better, probably. Okay, so you see this is the curve.
Yeah.
And you can ask, for instance, for the algebraic multiplicity. So this is 41. You can ask for the Milan number. This is, well, 2050, well, whatever. And you can ask to look at the topology of the optimal vector field, which is this way. So the gray point means here that this point is a component which is not invariant by the foliation of the vector field. And then the black point here is that the curve you have to, well, this is associated to the epsilon number that I introduced just before. And finally, you can, for instance, get a generic Turina number, which is a very important number for some theory. And this is this number. I don't know why, but this is just a computer, so it's difficult to interpret. So thank you very much for your attention.
Okay, thank you very much. Oh, there are some people. I have some questions. In fact, the questions that I was going to ask you, you answered in this example if there is any relation between the Milnor number and the Saito number, or the Turina number and Saito number. You computed these numbers in this example. Do you know if there is any relation between these numbers, the Saito and these two numbers, Turina and Milnor number?
There is actually, well, there is a relation, but between probably the Saito number and the Turina number.
The Turina number, yeah.
Yeah, probably. But the relation is probably very, very, very complicated. And probably this number can be understood, I think, more or less only generically, probably for a given curve. It's going to be very, very, very hard to obtain from analytical invariant, etc. So this is a very complicated number, as well as the Turina number is complicated.
Yes,
I mean, that number is not so difficult to understand. The Turina number is very, very difficult, and this number is going to be as difficult as the Turina number, I understand. And there should be some link between the two, but this link is necessarily is a very difficult link.
Okay, thank you very much.
Probably, yeah. If I may just one more remark about your question.
Yes,
the link
please.
is not going to be between just the Turina number of sigma and the Saito number of sigma, but between the Turina number of sigma and between the Saito number of sigma and all the curves that you obtain along the desingularization process of sigma. Probably.
Okay, okay. Are there any questions in the people from the internet?
I think there is a question.
Marcelo Escudero. Oh, Marcelo, hello. Please ask you the
Hello.
question.
It's nice to see you, Marcelo. It's nice to see you, Johann.
Yeah.
My question is, if you fix a topological class of a plane curve, okay? So you show in the fixed topological class, the Saito number, the maximal Saito number, is totally described using the multiplicity of the curve. And about the minimal, it's possible to describe the minimal Saito number in a fixed topological class in terms of the topological invariance?
Yeah, absolutely. This is absolutely possible. I think there is some work that has been done about this subject. But this is not very, actually this is just, the idea is to look at a tree like that and to make some combinatory things, to place some plates, to make some blue point in some sense. Well, this is difficult to answer your question, but the answer is yes. Just from the data of the reduction process, you can obtain the minimal number, the minimal minimal Saito number on the topological class. Yes, absolutely.
Okay. So then another question is, are all values between the minimal and the maximal Saito number achieved?
I would like to know. I really would like to know. I think this is a very difficult question. Okay. My intuition is that no, you cannot reach all the integers in the interval. There is there is some obstruction due to the presence of bifurcation component and so on. So my intuition is that you have some gap in this. But this is just like that, okay? Just an intuition.
Okay. Thank you. Nice talk.
Thank you.
Are there any questions in the internet? Sorry?
Maybe Jorge has a question?
Yes.
Jorge,
hello.
Please open your microphone.
Yes. No, my question is not exactly of what you have explained, but it's about the Saito module. You said that in general, in higher dimension, it's not free.
Yeah.
Saito module, but yes, I know. Are there some, let's say, some classes of hypersurfaces for which it is known that it is free? For instance, some kinds of coarse-ordinary hypersurfaces or things like this. I remember at some moment I was interested in that.
I think even
for explicit generators.
I think the question is
some specific basis.
sorry, there is some internet. Okay, so I think there is a, even in the case of the surface in C3.
Yeah.
The question is, I think, even for arrangement of hyperplane, the question is open.
It's unknown. Oh, it's open. Okay,
It's
even
open.
open.
So
Even
the
for
question
arrangements
of-
of hyperplanes.
Yeah. So
Even
the
for
question of
arrangements
the
of
freeness,
hyperplanes. Okay.
of the freeness of this module is a very, very difficult question. It has been studied
Okay.
in a global point of view, where you can use a tool from algebraic geometry and so on. There's
Yeah.
a vast literature, but the local point of view has not been so much studied, I think, as far as I know.
Mhm.
As far as I know, even in the case of just hyperplane in C3, the question is open. What
Okay,
we
so-
know is that it does not depend just on the configuration. It depends also on the precise position.
Yeah, yes, I understand, because the cross ratios or something like this.
Yeah, absolutely. There is some mysterious relation between the cross ratio that has to be used to, and that separate freeness from not freeness.
Yeah, okay. Okay, thank you.
Okay,
Thank you for the
thank
question.
you. I think we don't have more time for questions now, so please, let's thank you, the speaker.
Thank you very much. Thank you very much. I cut my.
We shall resume in 2 minutes, okay? Não são os três online hoje, né? Agora de boa pergunta.
Fernandez, Perez.
É isso. Só precisa achar o título da palestra.
Mas ele está aí já no.
Não faço ideia.
Ele é brasileiro?
Não. Eu não sei se ele é mexicano ou
Vocês conseguem ouvir, eu acho.
Mas ele não tá ali, tá?
Liga o microfone.
Aqui tá ligado.
Não, mas liga aí o microfone. Pode ligar? Pode. Você vai chamar ele? Qual é o nome dele? Fernandez?
Cadê o primeiro nome, Jorge? Não sei também. Eu não sei quem é. Esse eu não conheço. Os outros eu conheço todos.
The next speaker is here? Is there? Fernandez, Perez, are you okay?
Nem sei quem é.
Hello.
Hello.
Hello, Arturo. Nice to see you.
I'm fine, and you? How are you?
Fine, thank you. Are you going to show your presentation now?
Yes, I have.
Oh, it's time to begin. If you can present, I introduce you, okay?
Okay.
Yes. Now I'm going to introduce Professor Arturo Fernandez Perez from UFMG, Brazil. And he's going to talk about on the pullback of Levi-flat hypersurfaces. Thank you very much, Arturo, for your talk. You can begin.
Okay. Thanks to the organizer for the invitation. Today I talk about the pullback of Levi-flat hypersurfaces. This is this hypersurface is very interesting because these surfaces are foliated by complex manifold, but the hypersurfaces is real analytic hypersurfaces. Let us start. This work is in collaboration with Andrés Beltrán. Peru, da Pontifícia Universidade Católica, and Hernán Neciosud from the University of Peru, Pontifícia Universidade Católica too. The motivation, we are interested in the study of singular Levi-flat subsets, that is reanalytic subvarieties in complex manifold foliated by immersed complex submanifold. In this talk, we are consider Levi-flat hypersurfaces. Okay, this study has been initiated by Burns and Gong. And the concept of Levi-flat subsets have been studied by Marco Brunella, the first author to state the study of Levi-flat subsets. It's more general to Levi-flat hypersurfaces. In this talk, we focus in Levi-flat subset in the complex projective space. Okay. The first examples is very easy to construct Levi-flat subsets. For example, we take a J, complex surfaces, project surfaces, and T, reanalytic hypersurfaces on Y, X in the complex projective space, N bigger to 3, and consider rho, dominant rational map. Then you take the pullback of T by rho, the rational map, and you obtain H, Levi-flat subset. Okay, it's natural. The construction is natural to obtain a Levi-flat subset in complex projective space. Therefore, one natural question is, given a reanalytic Levi-flat subset H, under what condition H is given by the pullback of Levi-flat hypersurfaces in a projective complex surface via a rational map? What is the conditions will you necessary to impose to H? Giri-Leb in 2012 gave condition for an reanalytic Levi-flat hypersurface in Pn to be a pullback of a real algebraic curve via a meromorphic function. Okay. Gianni Bretas, my ex-doctoral students at UFMG, the Federal University of Minas Gerais, proved an analogous result from Giri-Leb for reanalytic subset in Pn. The main hypothesis in these works is that the Levy foliation has infinitely many algebraic leaves. Is the hypothesis in these works of Lev and Bretas, Gianni Bretas. Okay, it's a strong hypothesis in my opinion, but in the initial study, I consider with Gianni Bretas this hypothesis. In this talk, we have an answer to the question, assuming that H is invariant by a singular holomorphic foliation on Pn, a global foliation on Pn, with quasi-invariant subvarieties. This is a new ingredient. Okay. An irreducible complex subvariety S of complex dimension n is quasi-invariant by a global foliation on X complex manifold. If it's not F invariant, but the restriction to the foliation to S is an algebraically integrable foliation of dimension n minus 2. That is, every leaf of F restricted to S is algebraic. This is a new ingredient, okay? The concept of quasi-invariant subvarieties was introduced by Jorge Vittorio Pereira and Spicer in 2019 for codimensional holomorphic foliation on complex projective manifold to prove a variant of the classical Darboux-Yonolu theorem. Okay, it's a recently work, and the Jorge Vittorio and Spicer works with quasi-invariant subvarieties. Then the idea is consider these varieties to give an answer to the question. My result is the following: theorem, let H in Pn, n bigger to 3, be a irreducible real analytic Levi-flat subset of Levi dimension n. Levi dimension n is the dimension of the leaf on H. Invariant by n dimensional singular holomorphic foliation F. Okay, this is the hypothesis. Suppose that H is coherent. It's necessary coherence to construct global objects, and n bigger than n over 2. If the Levi foliation has infinitely many quasi-invariant subvarieties in the senses of Pereira and Spicer of complex dimension n, then there exists a unique projective subvariety X of complex dimension n minus n plus 1 containing H. To that, we have two options. Either there exists a rational map to P1, okay, P1, and there exists a curve C on P1, and the H is containing the pullback of C by R. Okay. Or there exists a rational map rho X and Y. H is containing in X, and Y is dimension 2. And there is a semi-analytic Levi-flat subset. Semi-analytic sets is a union of reanalytic sets or intersection or complements of reanalytic sets. Okay, and there exists T. Contained in Y, and you have this. We have this condition. And so we have two options because the hypothesis is the H is foliated by quasi-invariant subvarieties. This is the condition. The condition is natural because if you want the H is defined by pullback, this is necessary. The fibers of the rational map foliated the leaf. Okay. Remark: the hypothesis this hypothesis n bigger than n over 2 implies that the set is singular, has singularities. This is related to Neil Golfson paper. The authors proved that no singular reanalytic Levi-flat subset of the Levy dimension n exists in Pn. This is the word. Then this is an important hypothesis because H is for us is singular necessary. This is an interesting application. The main corollary, you apply the theorem to n minus 1, and we had the following corollary. Let H in Pn irreducible coherent reanalytic Levi-flat hypersurfaces invariant by a codimension 1 holomorphic foliation. Yes, I think this is H. Hypersurfaces, there is a foliation, a global foliation, F. If the Levy foliation has infinitely many quasi-invariant complex surfaces, then there exists a rational map of Pn to P1 and C real algebraic curve C on P1 to that the regular part of H is containing the pullback of the curve by the rational map. Or there exists a dominant rational map rho of Pn to Y. Y is projected surfaces, and there exists a semi-analytic Levi-flat subset T should that the regular part of H, the closer of regular part of H is contained to the pullback of T. Okay, the closure of the pullback of T. Two options. The proof of the corollary is very simple because you have the main theory. Okay, you apply the condition. This condition is equivalent to this condition. Particular n is bigger than 3 or equal 3. Thus, there is a unique projected subvarity X of codimension n containing H. Thus, you have two conditions. Since the dimension of X is n, we must have X equal to Pn, and we conclude the proof. So this is a nice application of theorem for Levi-flat hypersurfaces invariant by codimension holomorphic foliation. In order to provide a improvement of this theorem, we need to give condition to extend the Levy foliation on H, because if H is Levi-flat, H contains a Levy foliation inside the leaf L. But it's not true in general. The extension of L one holomorphic foliation, global holomorphic foliation, the ambient, for example, on Pn. In general, this is a problem of extension, problem of the Levy foliation on H. Okay. The ingredients is, I define the objects. Let M be a complex manifold of dimension m. A closed subset is a reanalytic subvariety of if every point in H there are real analytic functions with real values, phi 1, phi k, defined in a neighborhood, so that the h what u is equal to zeros set of the function. Okay. We denote the IH reg, the regular part of H. This is a subset of points where H is a real analytic submanifold of top dimension. Top dimension. Okay. This is a regular part of H. If H is a real analytic hypersurfaces, that is a real analytic subvariety of real codimension 1. For each point on regular parts, there exists a unique complex hyperplane, L. Okay. This defines a real analytic distribution of complex hyperplanes on the regular part of H. When this distribution is integrable in the Frobenius senses, we say that H is Levi-flat. It's equivalent to there exists a foliation on H, on regular part of H. This foliation is known as Levi foliation. Okay, H is the sets, hypersurfaces, and L is the foliation on H. In fact, the foliation of the regular part. And sometimes there exists a holomorphic foliation, global holomorphic foliation tangent to H. Okay. For example, if you take a real part of a holomorphic function, you take f a germ, for example, holomorphic function at 0, and consider the regular, the real part of f, and H is foliated, but the Nibel sets C, easy, con C real. And this foliation is tangent to the foliation defined by differential of f. Okay, and in this case, this is a holomorphic foliation. Because f is holomorphic. In particular, the Levi foliation extends to f. It is not true in general, okay? This is an example, a simple example of Levi-flat hypersurface. The leaf width is H or C. It's the Nibel set to C complex. Okay. Servolis Neto in 2011 proved that germs of singular foliations codimension 1 tangent to real analytic Levi-flat hypersurfaces have meromorphic first integrals, possibly holomorphic. It's a very important result to understand the Levi-flat hypersurfaces, because the foliation is very simple to study, because the foliation have first integrals. It's similar to the example, this example. Yeah, it's similar to this example. Locally, this is a germ, okay? It's locally result. We recall that no constant function F is a first integral. For a foliation F is each leaf of F is contained in the level set of F's. Okay, Levi-flat subsets, an irreducible real analytic subvariety H in M, where M is a complex manifold, okay? It's a Levi-flat subset if it has a real dimension 2n plus 1, and its regular part, H reg, is foliated by immersed complex manifold of complex dimension n. This is a generalization, the idea of Levi-flat hypersurfaces to higher dimension. Similar to the case of hypersurfaces, this foliation is called Levi foliation of H and will be denoted by L. The number n is the Levi dimension of H. We use the qualifier Levi for the foliation. It's leaf O and its dimension. I consider in this talk, I consider H is coherent. Coherence is by definition, the ideal of H is a shift coherent or coherent shift. Okay, the H is a variety, subvariety, okay? And you have the ideal of H, ideal shift of H. H is coherent if the ideal is coherent. This is it's natural to consider when you have works with global context. In particular, coherence implies that there exists the global complexification of H. This is Oka and another author's theorem, okay? A global complexification. The coherence hypothesis implies the following theorem. Theorem of Bretas, okay? Gianni Bretas. Let M be a complex manifold and H a Levi-flat subset of Levi dimension n. Suppose that H is coherent, then there exists an open neighborhood B of H and a unique irreducible complex subvariety X of complex dimension n plus 2. So there is a maybe H. So there exists a complex intrinsic complexification. There exists a X, a neighborhood B. Okay, is the dimension of X is n. The Levi dimension of the leaf here is n. Okay. The variety X is a small variety of complex dimension n plus 1 that contains H. We denote X, the intrinsic complexification, by HE. It's a notation. Levi-flat subset in complex projective space. Suppose H is a real analytic subvariety on Pn. Define the set town H with the cone whose points Z should tag you have the projection, say 1 plus 1 minus 2, on Pn. Okay, sigma. And you have the here, and you have the real algebraic complex conic. Okay, this is the lines containing in H. No? H is said to be algebraic if H is the sigma of a conic. The image. Okay. There exist many examples of this algebraic Levi-flat subset. In general, there exist no algebraic examples too. The construction, the following construction offers several examples of Levi-flat subset. For example, we take X, irreducible algebraic variety, and R, a rational function on X, and you take the pullback. So you have the Levi-flat, algebraic Levi-flat subset. And the complexification is X. The intrinsic complexification is X. Okay, then you take the X to P1. Consider the set of C and close it. This is containing X. Okay. And this is an intrinsic complexification of this set. Então, we add the hypothesis, the Levi-flat subset is invariant by singular holomorphic foliation in the ambient space. In this case, we have a reciprocal result. Let F a singular foliation on Pn tangent to real analytic Levi-flat subset H of dimension Levi dimension n. Suppose that H is coherent and the intrinsic complexification extends to real analytic subvariety, the hypothesis. If the restriction to HE has rational fixed integral, then the regular part, the closure or the regular part of H is contained to the pullback of the curve. Then you have a reciprocal result. The main hypothesis here is the foliation has rational fixed integral. In particular, there are infinitely many algebraic leaves. Okay. Now, but we need extend because the idea is following. We have H coherent, and then there exists a neighborhood B. In this neighborhood, there exists X, the complexification, but this is a locally subvariety. What condition you have the X extend to Pn? To Pn, maybe singular. For solve this problem, we need the Show theorem, extension Show theorem. Or aim is to extend the intrinsic complexification to an algebraic subvariety in Pn. To get this, we use the following extension theorem. The Show theorem, the famous Show theorem. The famous Show theorem says let's see a complex algebraic subvariety of dimension k and be a connected neighborhood C in Pn, then any complex analytic subvariety of dimension higher than n minus k in B that intersects C, Z, extend algebraically to Pn. We need another we fix C an algebraic subvariety, and any complex subvariety intersects Z with this condition extends to algebraically to Pn. We apply this result. And it's important to this hypothesis and this hypothesis, quasi-invariant complex algebraic subvariety. Okay, so this hypothesis and this hypothesis is necessary to conclude the intrinsic complexification of H extend globally to Pn. The proof is we take the L, a leaf. Oh, no leaf, not leaf. It's a quasi-invariant algebraic complex subvariety of dimension n minus 1. This is algebraic. It's containing H. This condition is equivalent to this condition, and we can apply the Shaw theorem. Okay, this implies H E extends algebraically to Pn. So the hypothesis is necessary to apply Shaw theorem. Consequence of Pereira, Jorge Vittorio Pereira, and Spicer theorem. The Jorge Vittorio Pereira and Spicer theorem is this theorem. Let F a codimensional holomorphic foliation and projective manifold. If F admits many quasi-invariant hypersurfaces, then either F is an algebraic integrable foliation or F is a pullback of foliation of dimension 1 on projective surfaces under a dominant rational map. So F is two options. F is algebraic foliation. The leaf is a rational map. Or the second is the pullback of G on rho. These are dominant dimension of A, Y is 2, and J is a foliation. Condition. The hypothesis that F has infinitely many quasi-invariant. The leaf, no? A foliation is quasi-invariant hypersurface. F is codimension of F is 1. Okay. We adapt this theorem to context of Levi-flat subsets. The consequence is this theorem. Let H a coherent, irreducible, coherent, analytic Levi-flat subsets on dimension, Levi dimension n, invariant by n is not codimension 1, okay? Singular foliation. Suppose that the complexification or intrinsic complexification of H extend to algebraic variety. if the Levy foliation has infinitely many invariant algebraic subvarieties of complex dimension n minus 1, you have two options. The restriction, the foliation is if E is equal to F restriction to H. This is a codimension 1 codimension with respects to the complexification of H is 1. And we apply the Perez-Spicer theorem to F to Fe. And we obtain the two options. Okay, this is I don't make the proof now. I prove the my theorem. Okay, the my theorem, the proof. The idea is first there is exists B neighborhood of H. Okay, there is exists intrinsic complexification. There is a unique complex. I denote HE of dimension n plus 1. In part, it's not difficult to prove the complexification is invariant by F. Okay. We use the hypothesis N. This hypothesis then quasi-invariant hypothesis to prove the the HE extends algebraically to Pn. We take the restriction of the foliation. The foliation Fe has codimension 1. Hypothesis admit infinitely many quasi-invariant subvarieties of complex dimension n minus 1. Apply the last this theorem. We have two options. Fe has rational first integral, or Fe is a pullback of foliation on projective surfaces. It's consequence of Perez-Spicer theorem. If the foliation Fe has a first integral, then there exists a curve, and H, the regular path of H, the closure, is contained to the pullback of C. In another case, is you have this map, and you take X by the complex intrinsic complexification of H, and it's not difficult to construct the T, because you have this condition, the pullback of G. This is implies this part. Okay. Well, and the reference is the works of Gianni Bretas. In this paper, the hypothesis is the algebraic leaf. Burns and Gong is the important works about Levi-flat, classical works. Brunella is the first author to state the definition of the Levi-flat subsets. Giri-Leb characterized the Levi-flat algebraic Levi-flat hypersurfaces via pullback of curves, real curves. The important work of the Pereira-Spicer, okay, is recently work. And Nick Wilson is the Lepsch's theorem for CR submanifold and non-existence of analytic Levi-flat submanifold. This condition is related to n bigger than. Thank you very much.
Okay, Arturo, thank you. Let's thank the speaker. Now we have time for questions. Are there some questions in the live people? If not, I will ask people in the internet if there are some questions. No, if there are no questions, we thank you, the speaker, again, please.
Thank you.
Thank you very much, Arturo. Very nice talk. We shall resume at 11 a.m. here hour in Brazil. Okay, now we have the coffee break. Thank you very much.
Às 11 a próxima.
Nossa, que pouca gente, né?
Hello, Andres. How are you? Bom dia, Michele.
Bom dia, Pepe.
Oi, Cidinha. Você chegou. Obrigado.
Oh, I'm sorry. I was speaking with no sound. I'm very happy to see you, happy to see all of you, Mehmet and all. Very nice.
Eu não sei ligar.
Não?
Ligou.
Pode falar.
Hello. Hello, Cidinha. Nice to see you.
Thank you, Marcelo. Nice to see you too.
Oi.
Olá, Pepe. Tudo bem?
Olá, Marcelo.
Pepe, eu já tenho uma
Sim, olá,
pergunta.
Marcelo.
Eu já tenho uma pergunta para fazer no fim da sua palestra. Aonde vai ser o próximo encontro?
Você já tem pergunta, mas ainda não escutou a palestra.
Sim, mas não importa. Eu já pergunto antes. Aonde é o próximo encontro? Precisamos definir aí que cidade do México vai ser, viu?
É legal. Olá, Jean Paul.
Bom, mas ele não vai falar agora, né? I think we can begin the talk, okay? Hello, now it's time to introduce Professor Pepe Seade. As you know, Professor Pepe Seade is from Mexico. He is one of the people that began this meeting on singularities a long time ago, okay? And it's a great pleasure for us to have you at least online. I was expecting you here, Pepe, but in few time you'll be here. And Pepe will give a talk. Sorry, I lost your. Are we going to present the talk, Pepe?
Yes.
Can you put the first page there, please?
Can you see anything? Because I don't see.
No, we have the We are seeing, but don't see your talk, only the presentation. You need to put the PDF file there.
I clicked in what says. Where it
No,
says
it's there. You need to
presentar.
find your talk, the PDF file, and put in your computer. Yes. Then he will talk on singularities, foliations, and groups
Okay.
of transformations. We have time, don't worry.
Okay. So now you can see correctly.
Yes, perfect.
Great.
Okay.
Great. Okay.
So
So
please, Pep, you can begin.
okay. So I'm very, very happy to be with you now. I would love to be in Victoria. That's a picture I took last time we were in Victoria. That was the picture from my hotel. And I'm missing you. But thanks for this opportunity. So there are three topics in my title: singularities, foliations, and groups of transformations. Almost every time I come to Brazil, I speak about singularities. A few times I've spoken about foliations. Now I'm really going to focus on the third point, which is very much linked to the previous two. So I will not speak, I will say a few words about foliations just to link them with the topic I'm going to speak about. So you let me recall that a manifold is a topological space in which we have an appropriate atlas, a covering by open balls, and each ball being a homeomorphism with an open set in Rn for some n. And if the atlas can be taken so that all the transition functions are differentiable or analytic or holomorphic, the manifold is in that category. And a foliation is defined by a foliated atlas, which means that our coordinate charts are foliated. So they are not only disks, say copies of Rn, but they are our Rn or our disk of dimension n is split into as a disk of dimension n minus k times a k disk. And the transition functions, the attaching functions, preserve this partition. This is the composition. So the figure indicates the picture. And then we have also singular foliations, which I will not define. I'm not going to work with them, but they appear very naturally. Let me give three examples where we have singular foliations. The one is what very much related with singularities. We have a smooth or analytic or holomorphic map from a n plus k dimensional manifold into an n-dimensional manifold, which is a submersion of an open set. And then the fibers of this map define a foliation on M, where the leaves of the foliation are precisely the fibers. And the critical points of the foliation give you the singularities. The critical points of the function give you the singularities of the foliation. That's an example. Another example is if you have an integral vector field on a smooth manifold, then the solutions of this vector field define a one-dimensional foliation. A third type of examples is if you have a connected Lie group acting smoothly on a manifold, then the orbits define the leaves of the foliation. And the singularities are the points with a special isotropy. Okay, so now I will move to the following point, which is groups of transformations. But in order to move there, let me mention two important ways in which foliations are linked with what I'm going to speak about. The first one is going to the example 2. There are some type of a special type of ordinary differential equations in the plane, which are called the Riccati equations, that Poincaré was investigating them, was working on them. And then these are second order differential equations on the plane. So at each point you have two solutions. And then he realized that as you moved along various closed paths on this space, the two solutions, when they return, they will be linked to the original solutions by a Mobius transformation. And if you will take the set of all these Mobius transformations, they will generate a group. And that's how he came into the theory of Kleinian groups, which is going to be the focus of my talk. Another way in which Kleinian groups appear is by looking, whenever you have a foliation, you can look at the transversal structure of the foliation. That means you have the leaves, you take a transversal of the complementary dimension, and then you take another transversal nearby, and you look how the foliation takes one transversal to the other transversal. And if you do that everywhere, you get what is called a pseudo group. Studying the transversal structure of foliations is a very, very important way to study foliations. And sometimes you impose a special condition on the transversal pseudo group. And you can study Riemannian foliations, you can study holomorphic, transversally holomorphic foliations, or you can study projections, foliations whose transversal pseudo group actually is a projective group, a group of projective transformations. Well, that brings us exactly to the subject I'm going to speak. So I'm going to speak about Kleinian groups. These were introduced by Poincaré at the end of the 19th century as the monodromy groups of foliations defined by certain differential equations, as I explained. It's a subject, a very, very classical subject, in which we have great names such as Alfors, Perez, Sullivan, Mosto, Deligne, Magnulen, and many others. So by definition, a Kleinian group is a discrete subgroup of PSL2C, the group of 2 by 2 of complex matrices of square complex matrices of 2 by 2 with the terminal 1, and the P means that you projectivize, that means you divide by plus or minus the identity. This group is actually the group of projective automorphisms of CP1, the complex projective line, which is this, by holomorphic to the two-dimensional, to the Riemann sphere. So let me look closer to this group. Well, first of all, let me say, I'm speaking about discrete subgroups. This is a group of complex dimension 3 of real dimension 6, which as a manifold is just SO3 times R3. So a discrete subgroup means a subgroup which is discrete as a topological space. So we have a discrete set of points in this torus, SO3 times R3, and that discrete subset forms a group. And those are called Kleinian groups. Originally, there was one more condition imposed by Poincaré to call them Kleinian. I will not mention that. I'll say it later. But for the moment, just like that, take that as our definition. So this group is by definition the same as SL2C divided by plus or minus identity. But there are many ways to see it. This is the same as considering the group of complex Mobius transformations. So transformations that take C, a complex number C, into A, C plus B divided by C, Z plus D. And it is also the same as taking the orientation preserving isometries of the real hyperbolic 3 space. And there are many other isomorphisms I will not mention now. And we have a preferred subgroup in it, which is the set of Mobius transformations with real coefficients, which is the same as taking SL2R divided by plus or minus identity, that is the group PSL2R. And that's also the same as taking orientation preserving isometries of real hyperbolic 2 space, and it is the same as the group PU11, and that is the same as isometries of the holomorphic, of the complex holomorphic line, hyperbolic line. Let me recall that Poincaré classified the elements in PSL2C into 3 types, which are, I have the drawings here, elliptic, parabolic, and loxodromic transformations. So an elliptic transformation up to conjugation is just like a rotation in the Riemann sphere. A parabolic transformation is up to conjugation is a translation. And the loxodromic element transformations they have up to conjugation, they have two fixed points, which we can think they are the north and south poles, and then all points move in circles somehow, or more generally doing this kind of, well, that's it. So up to conjugate, if you look, we look at the elements in PSL2C as equivalent slices of matrices, then the classification can be given in many ways. One way is to say that an element is elliptic if it is diagonalizable with unitary eigenvalues. It is parabolic if it is non-diagonalizable with unitary eigenvalues, and it is loxodromic otherwise. Let me recall also that every Mobius transformation is very elementary. It's a composition of an even number of inversions in the Riemann sphere, or inversions in the plane, including these reflections. Here we have a drawing for the inversion. And in this way, if we think inversions as transformations of the Riemann sphere, we see that every circle in the sphere is playing the role of a mirror. We are reflecting with respect to that circle, which is taking the circle is splitting the sphere into two parts, and the inversion is taking the inside outside and the outside inside. Okay, so this is very, very nice because it allows us to construct Kleinian groups in a very nice way, just playing. It allows us to have good fun. So we can start with any collection of circles in the sphere. We make the inversion in them. We take the index 2 subgroup of words of even length, and that's a Mobius transformation. That's an element in PSL2C. And every element in PSL2C is of that form. That's very nice. So by definition, as I said, a Kleinian group is a discrete subgroup of PSL2C, and that's an area of mathematics. Studying the geometry dynamics of PSL2C is a really, really rich area. I would say that it is a paradigm of both holomorphic dynamics and complex geometry. It's an area with tremendous richness because these objects, so many areas of maths come together there, and it's very, very important. Now, whenever you have a Kleinian group, this is splitting the Riemann sphere into two invariant sets. So you have a group of transformations, let me say an infinite group of transformations. Final groups classified as Kleinian, but they are not very interesting from this viewpoint. Let me take infinite Kleinian groups, and then you have an infinite group of transformations in the sphere, and the sphere is divided into two parts, which is called, one of them is what I'm defining here, the limit set. This is by definition the set of accumulation points of the orbits. So you take one point in the Riemann sphere, and you look at the orbit, and you see where it accumulates, and you do that for all the points, and you take the set of accumulation points of all orbits, and that is the limit set by definition. That's a closed set by definition, and it's invariant by definition. It is never vanishing unless the group is finite, just because every infinite sequence in a compact set has accumulation points. And its complement is by definition open. That's the region of discontinuity is called like that. And it is actually is the region where the group acts discontinuously. That means every point in the complement has a neighborhood that intersects only finitely many of its images under the group action. So we have this, then the Riemann sphere split into these two sets, the limit set and its complement. Let me see some examples. Here's one beautiful example. This is the triangle group 237. Here we have the unit disk in the sphere, and we take circles. So this group has three generators. Two of them, you can take them as the lines, two lines that pass through the center. Those lines intersect the boundary circle orthogonally. And then when we make reflection on those lines, the unit circle goes into itself. And the other generator is a circle. You can take it as, well, it's a circle that intersects the boundary sphere orthogonally and forms with the other two. The other two meet with an angle of pi/2. And this one meets the previous two lines in such a way that it forms an angle of pi/3 with one and pi/7 with the other. Okay? So we have this, and then we have these three generators, and we look at all the inversions that are composition of these reflections and inversions. And then the various images of the original triangle give us a tiling. They cover the unit disk, and they cover also the complement of the disk, which I'm not drawing here. I don't have it here, but they also come. I mean, this disk is the unit disk in the Riemann sphere, but the complement of the sphere is also tiled. Now let me take another example. This is a beautiful one. So Schottky groups, they have an analytic definition. I will not go into that. We can define them geometrically as follows. Take a collection of these joint circles and then make the inversions in that circles. And that's a Schottky group. Here we have an example of what they call a kissing Schottky group, because the circles are touching each other. I mean, the neighbors. And here I'm choosing the circles in a very, very specific way. So there's a circle C, which is orthogonal to all of them. Now, inversions have the beautiful property that if you make an inversion in two orthogonal circles, if you make an inversion in one of them, every orthogonal circle is invariant. It's not fixed point invariant, but is, as a set, is invariant. The circle goes into itself. So if we take this color of circles and we make inversions in each of these small ones, each inversion takes the circle C into itself. The circle C is invariant as a set. Yet, if you take one point outside all of them, far away, when you make inversion in one of them, the outside comes inside and the inside goes outside. So that point will come inside. And also, if you take one of these circles and you make the inversion in it, all the other circles will go inside. And so if we make a first iterative of inversions in all of them, we get that picture. But then now we can repeat, and we take a second iterate in each of them, and a third iterate, and we can just stop playing. And then we see that it's an exercise to see that first, all orbits, you can start with your favorite point in the plane, and that the orbit of that will accumulate in the circle. And not only that, you can pick any point in the plane that you want. You can pick any point in the circle that you want, and there will be a sequence of inversions in this color that takes the first point as near as you want to the other point. In other words, I'm saying that in this example, we can see geometrically that the circle C is the set of accumulation points of all orbits, and every orbit accumulates in all of C, and C is invariant, and every point in C has dense orbit in C. Okay? That's a very beautiful example. Now, what happens if we take our collar, we put it in our suitcase, and we go for a trip? And then when we go back, you will not have anymore a common orthogonal circle. It will be kind of moved. And then you get something like this. When you repeat the same game, it turns out that the set of accumulation points of the orbits is no longer a round circle, but a topological circle, which is a fractal curve. It's called what is called a quasi-circle. See, and in fact, it's a beautiful theorem of Bowen in the 70s that the limit set either is a round circle, a perfect circle, or if it is like that, it is a fractal curve, a quasi-circle. And it can happen that your color, your initial color, gets a little broken. If you separate the circles slightly, then the limit set becomes a Cantor set. Okay, so you have these possibilities. So, well, in general, limit sets have the beautiful properties. Some of them are this. One is that if the limit set has finite cardinality, then it consists of at most 2 points. And in that case, the group is called elementary. So an example is if we start with one Mobius transformation, and we just take the cyclic group it generates. Okay, if it is a finite group, if it is, an elliptic transformation, I said that elliptic transformations are rotations. If you start with an elliptic transformation and you iterate it, you repeat it infinitely many times, then you have 2 options. If it is a rotation by a rational angle, the group is finite and the limit set is empty. And if the rotation is by an irrational angle, then the limit set is everything. Every point in the sphere is a set of accumulation points of orbits. Now, if the element is parabolic, I say it is like a translation in the plane. And then in that case, the only limit point, the limit point consists only of the point at infinity. And if it is a loxodronic element, then you have 2 limit points. Well, those are and there are other groups more sophisticated, but which have only 1 or 2 limit points. Those are called elementary groups. If the group is non-elementary, then the cardinality is infinite, and and every orbit is dense in lambda in the limit set, and all the limit, and so on. And also, if we look at the complement, the region of discontinuity, this can be empty because the limit set can be everything. So, for example, if we take a closed hyperbolic 3-manifold, then its fundamental group is a subgroup of PSL2C, and it acts on the Riemann sphere in such a way that the limit set is everything. Okay, so the limit set can be everything, then the region of discontinuity can be empty, or it can have 1 connected component or 2 connected components, and if it has more than 2 connected components, it has infinitely many connected components. Okay, and there are many more properties I will not mention because we can spend a long time here discussing. So, as I said, each Kleinian group splits the sphere in 2 sets, invariant under the action, and then the dynamics concentrates in the limit set. If you do dynamical systems, you look at what's happening at the limit set. But if you do complex geometry, you look at the region of discontinuity, and that's a very, very beautiful set. The quotient of the region of discontinuity by the group action is a 1-dimensional complex orbifold. And well, there's a lot more we can speak. Let me say that there are some relations, interesting relations with singularities by work of Milnor, Dolgachev, and others. There's also by the work of Neumann. I will just say a few words about this at the very end. Now, let me move to higher dimensions. Then studying the geometry and dynamics of discrete groups of PSL n+1c acting on the projective space is a subject in which I've been working with colleagues in Mexico for more than 20 years. And I would say that it's a subject which is somehow in its childhood. And we can ask things like, why studying this subject? I will say more. And is there a notion of the limit set? What manifolds or orbifolds appear as quotients of the region of discontinuity? And well, many other questions. Many. I will discuss some of this, just an introduction to the subject. Well, why studying it? Let me say, firstly, it is a very, very natural generalization of the classical subject, which is extremely rich. So one should presume it is a rich subject. But let me say that it includes real hyperbolic geometry and complex hyperbolic geometry are included into this subject, just because SOM,1, which is the group of real hyperbolic isometries, is included in PU N1, which is the group of isometry, holomorphic isometries of the complex hyperbolic space, and that's just a group of projective transformations. So naturally, when you speak about the previous subject, you are including real and complex hyperbolic groups. Also, from the dynamical point of view, one can show that conformal dynamics actually embeds into the holomorphic dynamics of the groups, discrete groups of PSL n plus 1C. And when you work in the projective space, you can actually see more. And then, as I said, also there are important relations with holonomy of Riccati foliations, and also with the transversal structure of foliations. And finally, from the viewpoint of a uniformization problem, this is a very, very nice way to construct compact, complex manifolds with a projective structure, with a very rich structure, very rich geometric structure. So if you take an open set in Pn where the group acts properly discontinuously, then the quotient is an orbifold with a projective orbifold, and it contains a finite index subgroup which acts freely. So you have a manifold covering this guy, and then, well, so it's a nice way of producing complex manifolds, and in many cases, compact complex manifolds. So let me give you an example, which is how we actually came to the subject. Remember, I spoke about the Schottky groups before, which you would take these joint circles in the sphere, and each of them acts as a mirror and allows you to define an automorphism of the sphere into itself. And then having several such circles, you will produce Schottky groups. Here we take first a couple of projective lines in P3. So a line in P3 means the projectivization of a two-dimensional plane in C4. And if two lines are disjoint in P3, that means that the corresponding two planes in C4 are intersecting orthogonally, they meet only at the origin. Okay, so you can find a transformation in C2 taking one of the two planes into the other, which when you projectivize that, that means that you have maps in P3 interchanging the lines L and K. Whatever two lines they give you, you can find automorphisms interchanging them. And in fact, you have many automorphisms. And I can make this statement stronger. Take a tubular neighborhood of one of them. A carefully chosen tubular neighborhood. Okay, so these neighborhoods are of the form the line times a four-dimensional disk or a two-dimensional complex disk, because these projective lines are embedded in P3 with trivial normal bundle. So a tubular neighborhood is a product. So take one of these neighborhoods, and then the beautiful thing is that its boundary is S2 times S3, and that boundary serves as a mirror. That is splitting P3 into two diffeomorphic sets, and you have automorphisms taking the inside of the neighborhood to the outside, and the outside into the inside. And the thinner you take the neighborhood, the more dynamics you get, because then something very, very thin is being carried to something big, and that big is being very much contracted into something small. Okay, that's if you take any two lines, you can interchange them in this way. Now take finitely many pairs of lines, all of them disjoint, and sufficiently thin neighborhoods interchanging the interior, the exterior of these lines and taking one into the other. Okay, so when you make that game with whatever lines you get a discrete group. So, in fact, so you can forget about lines K, they play no role. Just take a finite collection of lines, projective lines, and take sufficiently small mirrors, sufficiently thin tubular neighborhoods, and transformations taking the interior to the exterior. Then what you get is a discrete group of automorphisms of P3. And you can really make a lot of, this is something very handleable, but very manageable that you can work with them. The complement is, sorry, the limits, in that sense, if you look at the lines and you look at the set of points where these lines accumulate, that is, I didn't write it, I think. Well, that said, the set of accumulation points of the orbits, which I didn't denote in lambda there, is a Cantor set times P1. And each line is dense in this Cantor, in this limit set. And then the complement is a region where the group acts almost freely. But it's not free the action, but almost. The quotient is a compact orbifold. But if you look at the words of even length, then that group acts freely. So if you take the complement of this Cantor set times P1C, and you take the index 2 subgroup of words of even length, then the quotient is a compact complex manifold. And well, that's a beautiful example. And let me say that these kind of examples generalize to all odd-dimensional projective spaces. So in P2n plus 1, you can take copies of Pn, disjoint copies of Pn, and do exactly the same game, and you get beautiful discrete groups in all dimensions, and beautiful compact quotients. And you can make a kind of Teichmüller theory for them. You can compute the dimension of the space of the infinitesimal deformations, and so on. Okay, now let me focus in complex dimension 2, where you can say more things. So the previous game doesn't work in P2. It works in all dimensional spaces. But now let me focus on P2. So for subgroups of P2, let me recall that when we are in the classical dimensions of in PSL 2C, so we are when we're looking at automorphisms of the Riemann sphere, the limit set is by definition the set of accumulation points of the orbits of points. It is also the complement of the region of discontinuity. It is the complement of the largest set where the action is properly discontinuous. It is the complement of the region of equicontinuity, and it is also the closure of the set of fixed points of loxodromic elements. That is, every non-elementary Kleinian group in PSL2C contains many loxodromic elements. Each one has two fixed points. If you look at the fixed points of all the loxodromic elements and you look at the closure, that is the limit set. So you have all these definitions of limit set in dimension 1. When you go to higher dimensions, it turns out that all of these make sense, but all the different notions do not coincide. So you have to choose which properties you want. You have to, there's not a canonical choice of a limit set. Now, there's always one notion of limit set, which is defined in a very, very general setting. And it turns out that when you're looking at P2, that's the correct notion. Okay, and when you look at P1, that notion coincides with the classical limit set. And this is what is called now the Kulkarni limit set. It was introduced by Ravi Kulkarni at the end of the 1970s. And let me motivate this definition with an example, because it can look strange. Let me motivate it with a simple example. Take the group of transformations in CP2 generated by this matrix. Okay, so with respect to the usual basis. So each eigenvector defines an invariant line in C3, So you have a fixed point in CP2. So this action in CP2 has 3 fixed points, which we also denote by E1, E2, E3. Now, 2 points determine a line. So each of 2 of these 3 points determines an invariant line, because if the fixed points do not move, then the line is invariant. So you have 3 invariant lines. Okay, and it's an exercise to show that the accumulation points of these 3 orbits, sorry, the accumulation points of all orbits in CP2 are these 3 points. So the orbits accumulate in these 3 points. The first one of them is an attractor, the second is a saddle point, and the third one is a source. It's an expanding point. Okay, then it is not hard to show that the group generated, this cyclic group, acts discontinuously on the complement of the 2 lines, but it also acts discontinuously in the complement of 1 line and 1 on the other point. And then, well, and then more things that I will not discuss more. But then that brings us, I mean, essentially what this is showing is that if you remove only the 3 points, which are the set of accumulation points of the orbits, then the action of the complement is not that nice, because the action on the invariant lines is not properly discontinuous, and you would like the action on the complement of the limit set to be properly discontinuous. Okay, so this example motivates the definition of the Kulkarni limit set, which is just defined as a union of 3 sets. The first one is the closure of the points with infinite isotropy, which in the previous case is the 3 points. So you take that as L0. That's your first set. Now, you look at the complement of these 3 points, and you look at the accumulation points of orbits of all other points. In the previous example, you don't get anything new. In other examples, you do. In this example, you only get the 3 points. But now you look at the complement, and you look at the compact sets in the complement. And you look at the set of accumulation points of compact sets. And then in that set, in that case, you can show that these 2 lines, the line E1, E2, and the line E3, E2, are the accumulation points of compact sets in the complement. Okay, so in that case, the limit set, the Kulkarni limit set, is the union of these 2 lines, and this is the Kulkarni region of discontinuity. That's a nice subject, because firstly, it's something which is canonically defined. Second, you can show that the action on the complement is always properly discontinuous. And third, you can show that also the equicontinuity region is contained always in this set of discontinuity. Okay, so it is a good set to start. And then I've been working with these colleagues in Mexico on the subject for some years, and then one can collect some properties of this set in the following. If you have any infinite discrete subgroup of PSL3C acting on CP2, and we look at the Kulkarni limit set, then firstly, that set always contains a projective line. Now, the number of lines is either 1, 2, 3, or infinite. If you have more than 3 lines, you have infinitely many lines in the Kulkarni limit set. And I didn't write it here, but if it has at least 2 lines, then the limit set is a union of lines. The only way you can have something which is not a line is when you have a fixed point in the limit set. But if you have 1 fixed point, then the limit set consists of 1 point and 1 line. And we can say, and the group is virtually a cyclic group. So one can really control a lot what is happening. Now, something which can happen is that you can, you can look at how many lines you have in the limit set. You can have 1, 2, 3, or infinitely many, as I said. But you can ask how many of them are in the general position. General position means that not 3 of them intersect. And then, so for example, there are examples in which you have a cone of lines in the projective, in the limit set, as many lines, lines parameterized by a circle, but all of them pass through the same vertex. So the limit set is a cone passing with one vertex and with base a circle is one. So in that case, you have infinitely many projective lines, but all of them have a point in common. So in that sense, in that case, we will say that only two of them are in general position. So if you look at lines in the limit set, they, in general position, we can show that there can be 1, 2, 3, 4, and if there are more than 4 lines, then there are infinitely many lines. And then in that case, it's very nice because it complements Kobayashi hyperbolic space, and you have many, many beautiful properties. And the point 4 is what I just explained before. And then regarding the number of connected components of the complement, you remember in the classical case, in P1, I said that it can be empty, or you can have 1 or 2 connected components. And if you have more than 2 connected components, you have infinitely many. In this case, it can be empty, or you can have 1 connected component, but we have examples where you have 2, where you have 3, where you have 4 connected components, and then examples where you have infinitely many connected components. We have not been able to show that these are the only possibilities. We have no examples with 5 or 6, but we cannot prove that these are the only possibilities. Now, some other properties of the limit set is, the first one, I mentioned it, if it has at least 2 lines, then it is a connected set, and it is a union of projective lines. So if it connects at least 3 lines, then the group has infinitely many loxodromic elements. I didn't give you the definition, but the definition of elliptic, loxodromic, and parabolic lines extends in exactly the same way I gave to higher dimensions. And if the limit set has more than 3 lines, at least 3 lines, then you have infinitely many loxodromic elements, and the limit set is the closure of the attractive loxodromic attractive fixed lines. The complement in that case coincides with the region of the continuity, and it is the largest set where the group acts properly discontinuously. And then a minimality property. Now let me look at the geometry. I'm done with the dynamic. Let me speak about the geometry. Now, first, some classical definitions. If you have a complex analytic manifold X and a Lie group acting on X, we say that the manifold has a GX structure. It has a maximal atlas with, if it is locally modeled by the manifold X with gluing maps in the group, attaching maps in the group G. Okay, and the same definition has to be more careful, extends to orbifolds. You can speak about orbifolds with a certain geometric structure. So some examples. If you take the affine group, then an affine structure means a maximal atlas where transition functions are open sets in CM, which are glued together by affine maps. You can speak of a complex hyperbolic structure with measurement circle atlas model on complex hyperbolic space of dimension n, glued by isometries of the space. You can have a complex projective structure, which is an atlas modeled by Pn, and all the transition functions correspond to intersections of elements of projective transformations. Now an observation, PUN1 and the affine group are both subgroups of PSL n plus 1c. So every affine and complex hyperbolic structure are automatically complex projective. Now let me mention an important theorem for surfaces. It's a theorem by Kobayashi Ochiai, proved in 81. Let M be a compact complex surface with a projective structure. Then M is complex hyperbolic or affine. For the previous statement I made, just by definition, essentially, every complex hyperbolic manifold has a projective structure. Same with affine. Here is saying the contrary. If the manifold for surfaces, compact surfaces, every projective structure is either hyperbolic or complex affine. Let me give a definition. Now let me look at this crystal group of PSL3C, which is acting on the Riemann on CP2. So the region of discontinuity of the action, if you look at the open sets where the action is properly discontinuous, you can have many connected components. We say that the group is quasi-co-compact if there is one open invariant set where the action is properly discontinuous and the quotient is compact. Okay? When this happens, the quotient is a two-dimensional projective orbifold. Okay, so I will say that the discrete group in PSL3C is elementary of type 1 if the Kulkarni limit set has at most 2 lines. Because I said that if it has, no, sorry, I should say at most 3 lines. I say that if it has more than 3 lines, then it has infinitely many lines. Okay, so and I say type 1 because you have a different notion of elementary groups. No. Theorem by Kahn and myself. If you have a quasi-compact group, then it is elementary of type 1. If it is quasi-compact, then it either is elementary of type 1, or it is affine, or it is hyperbolic. So it's very much in the spirit of the previous theorem. So the theorem said that if M is complex surface with a projective structure, then it is hyperbolic or affine. He's saying that if the group is quasi-compact, then either it is a finite subgroup of PSL3C, it's essentially, not quite, but essentially, or it is affine or hyperbolic. Then we can also say which open sets appear in PSL3C as open sets where the group acts properly discontinuously with compact quotient. These are called divisible sets. And then we have the complete classification. If we have an infinite quasi-compact group, then up to projective equivalence, the Kulkarni region of discontinuity is the maximal group where the group is properly the action is properly discontinuous, and it is either all of P2C of CP2 or the complex projective space regarded as the points in CP2 as an open ball in CP2. I will say more probably about this later at the end. Or is it CP2 minus 1 line, or CP2 minus 1 line and 1 point, or CP2 minus 2 lines, or CP2 minus 3 lines, or C star, that means C minus the origin, times H plus union H minus, which each of these is the upper or lower half space, or a hyperbolic open set in P1C times C star. Those are the only open sets that appear in CP2 as maximal regions where the group acts properly discontinuously with compact quotient. And then with that and more work, one can say more. Let me just recall some classical definitions of complex geometry. A Hopf surface means here I'm talking about compact surfaces. So a compact complex surface is called a Hopf surface if it is the quotient of C2 minus the origin by a free action of a discrete group. It is called an Inoue surface if it is the quotient of C times the hyperbolic disk divided by a solvable group. It is called an elliptic surface if it has a proper morphism over an algebraic curve with connected fibers where the generic fibers have genus 1. It is called a Kodaira surface if it has Kodaira dimension 0 and odd first Betti number. And it is called a primary Kodaira surface if it further has trivial canonical bond group. And then we have a classification theorem, which we have much more information. I'm just saying here just few things. The manifold, let M be an orbifold, this with a projective structure, a compact orbifold with a projective structure. So this is a theorem which is improving the previous theorem of improving and refining the theorem of Kobayashi and Ochiai, and also improving the previous theorem I mentioned by Klingberg. Suppose you have a compact orbifold, then it either is P2 divided by a final group, or it is a complex hyperbolic manifold, or it is complex affine, and we can say of which types. And we can say which type appears depending on the different open sets and groups and so on. So we have a very nice classification theorem. And let me just say a few words about singularities. Let me mention the Dolgachev quotient singularities. So I start with a discrete subgroup now in PSL2R, not C, but R. So these are automorphisms of, these are the isometries of the hyperbolic disk, of the two-dimensional real hyperbolic space that we can think of it as being, well, if it is PSL2R, I should have we should take it as the upper half plane, okay? And suppose it is co-compact. That means that the quotient of the upper half plane divided by the group is compact, okay? Now, this is a compact orbifold with orbifold singularities at the fixed points of the action, or the image of the fixed points. Now, we can extend the action of gamma to the tangent bundle of H, which is a trivial bundle, in the natural way. Is taking a transformation G acts on the upper half plane in the usual way as a Mobius transformation. So G times C comma W, where W is a tangent vector, goes to G times C, and then we take the derivative, which is non-zero, and we multiply by W. So we have a beautiful action on the tangent bundle. Obviously, I mean, the tangent bundle is a two-dimensional surface. Is H cross C, and it contains H cross 0, the zero section of the bundle. Then when we take the quotient of the tangent bundle divided by the action, it contains the orbifold H over gamma as the image of the zero section. So TH over gamma is a complex surface with singularities at the image of the zero section. Okay, and then the theorem is that the zero section can be blown down to a point, and what you get is a normal surface singularity with a very, very, very beautiful geometry. These are a special case of what are called the Dolgachev singularities. Okay, and examples of these are the 14 exceptional unimodal singularities of Arnold, and one of those 14 is this beautiful singularity that we all know. And well, one can try to mimic that in higher dimensions using complex hyperbolic geometry and so on. But I think one can say more, but this is a good place to stop. And muchas gracias, muchísimo obrigado.
Thank you, Pepe. Let's go to the questions now. Are there any questions here, presential people? No? If no, I ask if there are some questions in the people that is following online. Cidinha? It's your time for the question, Cidinha. The first time that you appear.
Thank you very much, Pepe, for the very nice talk. Yeah. So, yeah, I'm looking forward to talk about this with you here in São Carlos soon, right?
Yes.
Soon. Yeah, thank you.
Okay, thank you, Cedinha.
So, if there are no...
I think Andres has a question.
Yes, please. There is someone with Jean-Paul. You have some questions? I don't see, I don't listen you, Jean-Paul, please.
Okay.
Okay. So if there are no questions, we thank you, the speaker. Thank you very much, Pep, for your nice talk here.
Okay. Thank you. It was a pleasure for me.
We shall resume and open after lunch. Okay? Thank you very much. There is someone with the, I don't see, Christina. We can't hear you. We can listen you. I don't know. There are any questions? So by now we are finishing.
Marcelo?
Yes,
Isn't Nemeti perhaps has a question? No? It seems
I
that
think it
his
is
sound-
Nemeti. I think it is Andres, yes.
I don't know.
Yeah.
Oh,
Yeah.
but we don't listen you, Chris. No.
He sounds funny.
The Google Meet of I don't see his name. It's not good enough.
No.
I'm sorry. Okay. So we will finish now. Okay. And there is an open question yet that is when and where is going to be the next Brazilian, Chile, Mexico, and singularities meeting on singularities? Okay. I left this question to Maria Aparecida and to Pepe Seade to decide it and tell us, I don't know if not now, but later. Okay. Thank you very much.
I think it should be the turn of either Brazil or Mexico. I'm not sure.
Next time is in Mexico.
Jawed knows. I think Jawad knows.
Sorry.
Well, I think it is the time either of Brazil or no. Brazil is being now. So
Brazil is now. We need to do it in Mexico.
Then it is Mexico.
Yes.
It is in Mexico. Because the previous one was in Chile.
In Chile, yes.
Now
Next is
Brazil,
Mexico.
So the next one is Mexico.
Yes, you need to decide when and where, but what city, the country we know, okay?
Yes, okay.
Okay.
We have to discuss that.
Yes.
Yeah.
Probably we can decide it when you come here next month, okay?
Yes.
Thank you very much. So
we'll need some caipirinhas to discuss it.
Yes, the caipirinhas are waiting for you here. Don't you worry. Okay.
Very good. Very good.
So we will resume now and start after lunch. Thank you, Pepe. Thank you all.
Thank you all.
Bye.
Bye.